Hello, so this is lecture 4 on limits for my Calc 2 class. What I wanted to do is, I'm on sequences, excuse me. I wanted to evaluate a couple of limits of sequences here. Notice I've got two sequences given, and I want to find the limit as n goes to infinity of each of these sequences, determine if they converge or not. So let's look at this first one. The first thing to notice with this first one is that if I think of the function f of x equal 2x squared plus 1 over 3x squared plus x plus 2. Well, this thing here, the sequence, is the restriction of this to the natural numbers, right? From 0 to infinity. The integers from 0 on up. So if I can figure out the limit of this as x goes to infinity, now, it's worth noting that once we get used to this concept, we don't usually go over to the side and define f of x. We just look at this as if it is that f of x, right? But you've got to be a little bit careful, as we'll see in the next one. So that limit is 2/3 because the degree of the numerator and the denominator is 2. So it's just the ratio of the leading coefficients. So that means that the limit of the sequence that means the limit as n goes to infinity of the sequence must equal that limit 2/3. Okay, now let's go over to this other one. Now the reason I'm making a big deal of this function f of x is we have to be a little bit careful here. If I try to find this function, we have an issue. F of x equals -1 to the x times x minus 1 over x squared plus 2. What's the issue? Does anybody see what the issue is? I'll give you just a moment. Boom, 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 boom. Anybody get it? Yeah, it's that -1 to the x. What is, well, -1 to the 0 is just 1. -1 to the 1 is -1. -1 to the 2 is 1, and so on down the road. But the issue with this is that it's not defined for a lot of those x's in between the natural numbers. It's defined for the 1/3, right? -1 to the 1/3. That's a cube root of -1. That's defined, right? That's -1. However, the square root of -1, remember, we're working in the real numbers. We don't have the square root of -1 defined. This is not a situation that we really want to work with. That's out of the question. However, let's look at it without the -1 to the n. If I look at this function, at the limit as n goes to infinity of just this n minus 1 over n squared plus 2. Well, this is just like the limit above, right? This is just a rational function, n and n over degree 1 over degree 2. And of course, that is defined for, that is the restriction of some function on the reals. And so we can evaluate that limit. And of course, what is that limit going to be? It's going to be 0, right? Because the degree of the numerator is 1, the degree of the denominator is 2. So what's happening here? Let's look on a line here. We have an alternating series. So if I look at this thing here, if I look at without the negatives here, let's do that in green, what we've got is a bunch of points heading in towards 0, right? But that -1 makes them alternate. So when they alternate, we got a positive. Let's make that this way. We got a positive, right? And then it goes over to a negative. And then we get a positive, and then it goes over to a negative. Then we get a positive and a negative and a positive and a negative and positive and negative. In other words, it's bouncing back and forth, but it's still zeroing in on 0. So we still get to say here in this limit, as n goes to infinity, of -1 to the n of n minus 1 over n squared plus 2 is equal to 0. So that limit actually exists. But now let's try another one. Okay, so let's look at this sequence here. This is just like the first sequence we looked at up here, except for we've got that -1 to the n there. Do you remember what that first sequence went to when we did the limit as n goes to infinity of 2n squared plus 1 over 3n squared plus n plus 2? Yeah, that was just 2/3, right? So what's happening here when I have that -1? Well, this thing here, this portion right here is getting closer and closer to 2/3. So if I start alternating the signs, what's going to happen? You're going to get, the positive ones are going to get closer to 2/3. The negative ones are going to get closer to -2/3. It's going to bounce back and forth between getting closer to 2/3 and closer to -2/3. So this particular sequence here, this one diverges. It's not gonna zero in on anything. It's gonna bounce back and forth between +2/3 and -2/3. In fact, we have a nice theorem here. Let me get that theorem. The sequence -1 to the n an converges where n, sorry, let's get that where n is, an's positive. It converges if and only if the sequence an converges to 0. Okay, so with alternating series, it's not too bad. Okay, so now let's look at this sequence here. This sequence is a little bit weird because, well, if we go to define the f of x, let's just put this down and see if we can make sense of this. It's a lot like the last thing we just looked at. If we try to define this as a function of the reals, not just the natural numbers, well, what's wrong with this? What's wrong with this is, what does that x factorial mean? What does 1/2 factorial mean? What does, pi factorial mean? We don't have any meaning for that. In fact, there might be ways to define it, but it's certainly not the same way we've defined it here. And so we're not, it really is beyond our means here. We're not going to deal with this situation at all. This is another case where we don't want to look at this. So how are we going to evaluate this limit? Well, I mean, we could do a heuristic argument and say, let's list these out. If we start listing this sequence out, we get 0 when n equals 2. I get 1 over 2 factorial, which is 2. I get 2 over 3 factorial, which is 6. 3 over 4 factorial, which is 24. 4 over 5 factorial, which is 120. And you can kind of see the denominator is getting bigger a lot faster than the numerator. What does that suggest to you? Yeah, it suggests that you should be converging to 0. And that, for most of the time, that's actually a reasonably good argument. But let's see if we can get this a little bit more precise. And that's going to bring in another theorem anyway. Let's look at n minus 1 over n factorial. Well, one thing is that's always bigger than or equal to 0 for n bigger than or equal to 1, right? And another thing is that's going to be less than n over n factorial, right? Which, well, what is n over n factorial? That's going to be n over n times n minus 1 factorial, which of course is 1 over n minus 1 factorial. This is a lot clearer. one in the numerator, this first one we started with is actually of the form infinity over infinity. And even though we can kind of see the denominator takes over by listing a few terms, it's an indeterminate form. It's an indeterminate form. So theoretically, that could go to anything. But this thing here, this 1 over n minus 1 factorial, what's happening to that? Well, that's of the form 1 over infinity, right? Because n minus 1 factorial is just getting bigger and bigger and bigger. So what's that going to? That's going to 0. Okay, so sometimes you can, so this thing here is going to 0, and this thing here is trapped between 0 and this, so it must go to 0 as well. And this brings another very important theorem called the squeeze theorem. I love that name. It makes me think of Mama's got a squeeze box. Okay, I won't sing for you. Okay, the squeeze theorem. If we have 3 sequences, an less than or equal to bn less than or equal to cn for all n, or really for all n past a certain point, that's good enough, then, oh, and the limit as n goes to infinity of an equals L equals the limit as n goes to infinity of Cn, then what do you think we're going to say? Then Bn gets squeezed to the same thing, right? Then the limit as n goes to infinity of Bn is equal to that as well. So the sequence consisting of the constant 0 goes to 0. The sequence that this is less than, n over n factorial, goes to 0. Therefore, this thing here goes to 0. And we're done. All right.